Hi, welcome to another edition of Calculus 2. Today we are going to talk about series and convergence, and we are going to focus on the most important series, which is the so-called geometric series. Let's go ahead and take a look at this problem. Okay, the most famous example of series, as we said, is a geometric series. This is the famous example of the geometric series. As you see here, we are adding a sequence of numbers. These are all fractions. Denominators, you notice they are all powers of 2. You go from 2 to 4 to 8 to 16, and guess what's the next number. Of course, you guess it is 32, and so on. Coming across the problem like this, we face several questions. First of all, what's the sum of all these numbers? Perhaps you can guess what the sum is going to be. Maybe you can crank up your calculator and add a few terms of this series and come up with an educated guess as to what you think the answer is. What's the sum of this? As we come across more complicated examples, we start to think, what does it mean to add infinitely many numbers to each other? Is it just as simple as adding the numbers on a checkbook, or are there more subtle issues involved? Of course, we suspect that this issue of infinity is going to give us some pause as to what do we really mean by the sum. Next question that comes up is, if somebody writes a series, can we always come up with a so-called formula for the sum? Is there always a magical way of arriving at a clean-cut answer and such? Next question comes up is there always a sum? If you add up a bunch of numbers, do you always get some definite answers? Is there any puzzles in that area? And as the issues pile up, the question then typically comes up, why do we study this topic? Where is it headed, and what do we do with that? Here I have written some other examples of series. You might take a second or so, look at them, see if you can come up with a kind of a conclusion different than what you had over there. So first one, 1, 2, 3, and 4, and 5. If you add them, what you suspect is going to happen, you notice that, you just keep adding bigger and bigger numbers, and it does not settle down to anything the way, if you have experimented with this one, the experience here is very different from that one. Here is another kind of a puzzling situation. What if you add and subtract and add and subtract the same number? What happens there? You try it, you see, I have 1, and then I get 0, and then 1, and then 0, and 1, and 0. So it keeps going on like that and doesn't settle to any particular number. So this one is headed toward infinity. This one flip-flops between zeros and ones. If you add these terms, we say we are doing a partial sum. First one is just 1. Let's just practice it. First one is just 1. If you add 2 of them, you get -1. If you add first, second, and third, what do you get? -1 and 3. That's a 2. First, second, third, and fourth, we get -2. What do you think we are going to get next time around? If you guess that we are going to get 3, you are on the right track. And next number we get -3, and so on. So when we are alternating the signs and adding up just the natural numbers, we get this peculiar pattern of the so-called partial sums. So what we are doing here is these are partial sums. Partial sum simply means going so far into the series and add them up and see what you come up to there. So we see that we are fluctuating, the sign flips, and not only that, we see a behavior like the first one, that it also gets, the numbers get large and also fluctuate. So in these three cases, it stands to reason to say, these obviously do not converge, meaning the sum is not approaching a particular number. They have, this one is going to infinity, this is flip-flopping, this is flip-flopping and also going to infinity. How about this one? Well, this is another famous series, a bit more complicated than the first one. It's just sum of the reciprocal of natural numbers starting from 1. What do you think? If we add up all of these things and keep going, does it settle down to a number? Does it exceed every number? So I invite you to experiment with that and then come up with some guesses as to what is happening in this case. Now I'm going to leave that to you to work on, and let me just do another one. Here's a nice picture for displaying one of these geometric series. Well, you notice that I have taken a square that is each side of it is 2 by 2, so the area of the whole square is going to be 4. We have divided it to 3 colors in this particular manner, that we take it and cut it at half points. So each of these sides is going to be not 1, and area of each of these biggest squares is going to be 1. Next one, well, we are taking this one and dividing it by 2 on every side, so each area is going to be a quarter. So this yellow is going to be, this is a quarter, this is a quarter, that's a quarter. And then next time around we get a square that is half as big as this one. So by now this was the side of the square was 1/2, and we repeat the pattern. We take this and divide that by 2, and so the side is going to be 1/4 and so on. So now the area of each of these colors is going to be 1/16. Now let's go ahead, add up all the areas. Of course they should all add up to 4 when we are all done. We notice that the yellow and the blue and green occupy the same amount of area. This is 1, this is a quarter, this is 1/16. This is also 1, a quarter, 1/16, and so on. So we get 3 of each, so I have 3. The first area of the big ones is 3. And the next one is 3/4. The next one is 3/16. And well, the next one is going to be a quarter of that, so it's going to be 3/64, and so on. Well, the sum of all these areas has to add up to the area of the large square, which is 4. So here is a geometric proof that the sum of this particular series is 4. Now let's go ahead and write a concise formula that shows the same formula. So I would indicate that I'm doing a summation, so I write sigma for sum, just as you did in calculus 1. Then I consider the terms of this sequence, these numbers. I'm going to try to come up with a formula for them. So of course the numerator of all of them is 3, so just write 3. Denominator is power of 4. So if you wish to think about it, is the first one is the exponent is 0, if you wish to think about it like that. Then 4 to the power of 1, 4 to the power of 2, 4 to the power of 3. So I can write 4 to the power of n. N is a number that starts from 0 and goes all the way to infinity. So this is a concise notation for a series, and with this demonstration we see that the sum of this happens to be 4. Okay, there are many geometric proofs of this type, and I'm going to ask you to come up with a proof by yourself. Why should this be the number that you thought it is? So first of all, come up with a guess what this thing is, and then come up with a picture that shows your reasoning. Okay, We are going to go after the main topic, which is geometric series in this section. So we said this is the most important geometric series. Okay, geometric series always starts with some number. Like for example, here we started with 3. Over there started with 1/2. There's always a first number other than 0. We start with that number, so some number, let's call it a, and then each subsequent number is the same multiple of the previous number. So for example, here you notice that each number here is a quarter of the previous one, and this is a quarter of that, this is a quarter of that, and so on. In the first example, each of these numbers is a half of the previous one. So that multiple traditionally is referred to as by the letter r. So let's write, so the next number is r times the previous one, and the next number is r times this, so we are going to write ar squared, and the next number is r times this. What would be the exponent now? If you said 3, you are following the lecture. So, and the next one is ar4, and so on. Now we want to write an abbreviated notation for this. We say, well, we are doing a summation. Each term of series, we need to come up with the formula for the term itself. So we write ar to some power n. Now we have to take n and match it to actually what happens here. In this particular situation, we are starting with power 0. R, remember, r to power of 0. You remember that from algebra is just 1. So you can think about r to power of 0, 1, 2, 3, 4. So I say the exponent is starting from 0 here and goes to all the way to infinity. So that's a notation for the geometric series, the formula for terms of the geometric series. As we said, in all of our examples, we start with a different from 0, so that we wouldn't be talking about a trivial situation. If a was 0, all these numbers would be 0, and well, the sum would be 0. We have a number r that is involved here, and we refer to it as ratio. That's a ratio of the geometric series. Now, in this case, we have a geometric series. What's the first number? A is 3. What's the ratio? The next to the previous, the ratio is a quarter. Now, next question comes up. Well, with this picture, we could figure out what the answer is, but what if I had some random number a and another random number r? There are pictures for those things too, and you can read it about it in your text, but let's just do the algebra proof that tells us what is really going on. The method builds on the concept of a partial sum. We already partial sum of a series is the sum up to a term number n. So here, for example, my first term is this is first term, this is a second term, and third term, and so on. So I write a partial sum s number 1. The first number is just a. Second number is a plus ar. Third sum, or third partial sum, I go as far as r to power of 2. So when this is 3, that's 2. So if this is 10, that is 9, and so on. So if I want to go at n terms starts with power 0 and goes on all the way. And what would be the power of the last term? Okay, so we look at the sequence here and see that 1 and 0, 2 and 1, 3 and 2. this has to be n minus 1. It stops 1 short of what this thing is. Okay, by the sum of a series, we really mean the limit of the sequence of these partial sums. That's the official definition of series. The limit of the partial sums is the series sum itself. Now, to achieve a formula here, we just do a simple algebraic manipulation. I go ahead and write R times Sn. Let's see what happens here. When I multiply my first term by R, so I get AR. When I multiply the second term by R, I get AR squared. And let's write another term here, maybe AR squared. If I take this one and multiply by another R, I get AR cubed. And so on it goes. Every time I multiply by R, the exponent of my R goes up by 1. So the last one is going to become A to power of AR to what power? So it's going to go up by 1, so it becomes power n. Now we are going to do a very basic algebraic manipulation. We see this is same as that, so like this is same as this. This is same as that. If I had written the third one here, that would be same as this one, and so on. That gives us an idea. If we subtract these two expressions, all these common terms are going to disappear. They are going to cancel each other out. That's referred to as telescoping summation, when you add things and these two cancel each other out. So that's what I'm going to write here. I'm going to write the first one Sn minus R times Sn. So I'm subtracting these two. When I subtract these terms, A stays, these two cancel out, these two cancel out. This one is going to cancel with the one just prior to this. Prior to this, there would have been AR to the power of n minus 1. They are going to cancel each other out. And this is going to be the last term that's going to, last man standing here is AR to the power of n. Make sure you understand what happened in this subtraction, that this is the answer, the result of subtraction of these two. Well, we want to calculate Sn. Easiest thing to do is to factor Sn, and then now I have A minus AR to power of n. I can divide by this parentheses. I see that Sn, I have a formula for Sn. So that's a grand achievement by itself. The sum of n terms of a geometric series that starts with A and goes up by a factor of R every time is given by this formula. Now, once I have my partial sum, I ask the question, what is the limit of the partial sum? That is, what's the limit of Sn as n goes to infinity? After all, remember, Sn is sum of n of these things. If you let n go to infinity, you're summing them, all of them. So here's S1, S2, S3. As you go down, you're including more and more of these terms. If you go to S infinity, you have included all of them. So now we are asking, well, what's the limit of Sn? Well, A and R, and this A, these are all fixtures. The only place where things are changing is where this exponent shows up. So everything revolves around what is R to power of n going to do. If R is a number larger than 1, well, of course, powers of that is going to go to infinity. So we are sure that if R is larger than 1, then Sn is going to go to infinity and the series is going to diverge. So a series, we call it a divergent series if it does not converge. Now, what if r was a number less than -1? Same issue is going to happen. Like if r was -2, -3, and so on, when you raise it to larger and larger exponents, what it does is that it fluctuates between plus and minus, and also its magnitude goes to infinity. Okay, so with respect to these two, we know that these are larger than 1 and are less than -1 is going to be problematic for us. They are going to, this one causes the partial sum to go to infinity. This one is going to fluctuate and go to infinity. What if we take r to be exactly 1? Well, if r is exactly 1, you're dividing by 0. You know that is a problematic thing to do. If you go back here and say r is equal to 1, well, you're adding a to another a to another a to another a, and so on. And of course, remember, we assume that a is non-zero. You are adding infinitely many a's. You still have a situation where your numbers are not going to converge. So r equal to 1 is not going to converge. If r is equal to -1, same problem. If you have r is equal to -1, you will have a. What is this going to be? If r is -1, that's going to be minus a. Then this one's going to be plus a, minus a, and so on. That's going to be a situation like this example. You had 1 -1, 1 -1, and so on. In this situation, you are going to have a minus a plus a minus a, and so on. So that series would not converge either. So in all these cases, something goes wrong and the series would not diverge, it would not converge. We call it a divergent sequence. Divergent series. What is left? Well, if r is between 1 and -1, if r is a small number between 1 and -1, when you raise it to higher and higher exponent, this thing is going to go to 0. If r is between 1 and -1, then r to the power of n goes to 0. Another way of saying that is r in absolute value is less than 1. So if r is less than 1, this expression goes to 0, and all we are left with is a over 1 minus r. The limit is a over 1 minus r. This applies if r is less than 1. Otherwise, we said the geometric series a r to the power of n. Let's rewrite this result. It's equal to a over 1 minus r if r is less than 1. Otherwise, it diverges. It diverges for r larger than or equal 1. Different kind of phenomena shows up for these 4 cases, but all of them fall under the same terminology or same umbrella. All of them results in a divergent series. Okay, of all the results that we are going to have for our series, this is going to be the most important, and I want to make sure that you understand how it came about, what it means, and so on. We are going to have plenty of results on series, and it's kind of hard for a student to absorb all of it, and in many cases students finish the course and go on to calculus 3, and then they don't remember much of anything from this section. Okay, what you want to do is try to understand what is behind the concepts. What does it mean? And there are going to be a bunch of formulas and such that you try to memorize, but the important thing is to understand what is referred by each of those formulas. Okay, so our first important result is just what we wrote. The case of the geometric series, all the cases are considered here. Let's just go ahead and make sure we see an example. So we said in the example below that sum of a r n starting from 0 to infinity is a over excuse me, 1 minus r if r is less than 1 in absolute value. So in this case I have a is equal to 3, r is obviously less than 1, and I have 1 minus r in the denominator, so 1 minus 1/4. So what do I get? 3 divided by, this is 3/4. Well, when you divide that number by this fraction, you just get 4, which is the answer we had by just looking at that picture. So that picture reproduces what we are getting from our formula. Let's go ahead do another example of a series here. Sometimes you see perhaps in your high school classes and such, and that is the case of repeating decimal problem. Well, you remember from, like, maybe from elementary school, if you look at certain fractions, you see a kind of a repetition. The most famous one would be 1/3, of course. It's a string of 3's show up. Of course, if I look at 1/30, there could be some leading numbers that don't repeat, but then repetition starts down the road. One of the intriguing cases is 1/7, 142, 857, and then 142, 857 again. So if you look at this thing, you see that this set of numbers show up in your ratio when it's written in decimal. So the notation for this is to take the portion that repeats itself and put it under a bar to indicate that is the portion of the decimal number that keeps repeating itself. Now, a question comes up: if I give you the number on the right hand side, can you figure out for me what is the number on the left hand side? Let's do a simple example. Suppose I give you a number, call it x. Let's write it, say maybe point, say 21, 21, 21, and so on. The question is, write x as a fraction, as a rational number. Write x as a rational number, which means write it as a fraction. We can do this thing one of two ways. One, I'm sure you have seen this in high school. Another one is applying the formula we have just seen. In high school, perhaps you would have been told to approach it like this. Just look at the length of the cycle. The cycle has two numbers in it. So multiply by that power of 10. So in this case means multiply by 100. So when you multiply by 100, the decimal point is going to jump, and now the interesting thing is that the numbers after decimal are the same. So if you subtract these two, if you take this and that, subtract them, so now you have 100x, and that was x. If you subtract them, of course this decimal cancels that decimal, you have 21. So now you have 99x is equal to 21. So x is 21 over 99, which you can of course simplify a bit, divide by 3 here, and say get 711, and then you're done. Okay, how is this related to the issue of geometric series? Well, I can go ahead and say, okay, this x, 0.21, 21, 21, and so on. I can write this thing as, well, this portion is 21/100th. This portion is 21 on 10,000. And this portion is 21 out of 1 million, and so on. Or to write it in a more intelligent way, this is 21 over 10 to the 2. This is 21 over 10 to the 4. This is 21 over 10 to the 6. Okay, now we realize this is a geometric series. The first term of it is 21 over 10 to the power of 2, and the ratio is a ratio of each to the previous one. You have to take any of these things and divide by the previous one, see what you get, or ask yourself, what should I multiply this with to get the next one? Of course, I have to multiply by 1 over 10 to the power of 2. Okay, you might want to make sure you are getting R correctly and not upside down. So x, or the sum of our series, x is going to be a over 1 minus r. So it's going to be a, which was 21 over 10 to the power of 2, over 1 minus 1 over 10 to the power of 2. To simplify, multiply everybody by 10 to the power of 2. Numerator you have 21, denominator have 10 to the power of 2 minus 1, and this is 21 over 99, which is exactly what we had before a moment ago. So that is the conversion. Another example of problems that come up here, and it's going to be in your exercises, but it is not related to geometric series, nor is it that it has that much of a significance, but just to have another example of a series other than this most important one that we were just looking at, is an example of a so-called telescoping series. Telescoping series is more of a exercise on things you have learned before, in particular partial fraction decomposition somehow shows up here again. So let's just take an example. Suppose we ask the following question: find the sum of 2 over 4n squared minus 1. Here we might start n at anywhere we want. Let's just start at 1 and go to infinity. So what is this series? Let's just go write a few terms of it so it doesn't look like a mysterious thing. 2 over, okay, if n is 1, this becomes 4 minus 1. If n is 2, well, this is going to be 16 minus 1, this is 15. And the next one is going to be 3, so that's going to be 36 minus 1. And the next one is, of course, number 4, so it's going to be 16 times 4, 64 minus 1, 63. So in some problems, it could be that they give you a series like this, and first you have to work your way to that form and then follow the discussion after that. You look at this thing, you notice that it is not a geometric series. Like this is 5 times that, but when you take the ratio of these two, you get what? You get 7 over 3. It doesn't have any resemblance to geometric series anyway. So it's an entirely different issue, and it's one of the examples where we can actually find what the sum is, but it is mostly because of a lucky coincidence than anything else. Now, where does partial fraction decomposition come in here? So let's remind you from the section on integration, partial fraction decomposition. This concept, this tool comes in lots of places. So over there perhaps you would have written your formula like this. Let me just use the same notation, 4x squared minus 1. Whatever variable you want to write here is fine. You remember that we could go ahead, over there the issue was how do you integrate this thing. We were breaking it up in smaller fractions so that we can find the formulas easily. Here I see that my denominators has to be 2x minus 1 and then 2x plus 1. It's just that I don't know what's the numerator, so we had these unknown coefficients in the numerator, and then we go ahead and find out. How do we find out? We put these two fractions together again, we add them up, so 2x minus 1 times 2x plus 1, and then I'll have a times this, a times 2x plus 1, and b times 2x minus 1, and then the numerator now is 2x times a plus b, and then a minus b. Over denominator is just 4x squared minus 1. Okay, for this to match my first term, I need to have my a plus b to be 0, and then my a minus b to be 2. Obviously the solution now is going to be a is 1 and b is minus 1. Okay, you have seen this problem before, so I leave the details to you before. How does this decomposition goes? It's going to be 1 over 2x minus 1 minus 1 over 2x plus 1. Well, of what use is this partial fraction decomposition? Okay, suppose you did this. What now? Well, it means that each of these fractions can be broken into a pair, and something magical happens when you do that. So for example, if n was 1 or x is 1, your fractions are 1 over 1 and 1 over 3. So this one I can write it, this is 1 over 1 minus 1 over 3. Obviously if you subtract it you get 2/3. This case applies to x equal to 2. So if x is equal to 2, the first one is going to be 1 over 3, and the second one is going to be 1 over 5. This is 1 over 3 plus 1 over 3 minus 1 over 5. Let me write my 3 better. And then how about here? What do you think that's going to be? Now n is equal to 3. N equal to 3, this makes 1/5 and this one makes 1/7. Do you see the magic? What is the significance here? Well, the significance is this minus 1/3 and this plus 1/3 cancel each other out. It's minus 1/5. I guess I made a mistake here. Let me correct myself. So here n was 3, and it was 3. The first number was 5 and second number was 7. So I made a mistake there, and here's a correction. Okay, 1/3 cancels this 1/3, minus 1/5 cancels this plus 1/5. There's a minus 1/7 here and cancels the next one, and so on down the road it goes. You might be wondering about what about the last one? Well, the last one is getting smaller and smaller as you go down this list. Who is the last man standing? Last man standing is just this, the first one. One is standing, and all these are going to cancel each other out. And that is an example of what is called telescoping summation, because it's kind of like a collapsing telescope or some kind of ladders or various other devices that you just collapse it on itself. These two cancel each other out. Okay, there is a lot more to say. Some of what we want to say are theoretical type. Let me postpone that to a short lecture that's going to come up after this introduction. So that's going to be our approach. We are going to start with something that the discussion is going to be simple top follow if it's possible, and then we collect theoretical discussions in one place, and that's going to be like additional next level of reading, if you wish. Okay, until our next lecture, good luck and God bless.